Next, we'll look at the Clausius Clapyron equation. And in this equation, we're relating vapor pressure to temperature. Remember from a vapor pressure curve that vapor pressure is related to temperature, not linearly, but exponentially. So vapor pressure increases exponentially as the temperature increases. And that's given by the vapor pressure is equal to beta times e to the negative delta H of vaporization over RT, where beta is a constant that's dependent upon the particular substance in question. So if we do some mathematical manipulation, we can derive an equation where we can relate vapor pressure to temperature in the form of a line, where the Ln of vapor pressure is equal to negative delta H of vaporization over R times 1 over the temperature plus Ln of B, where Ln of B is the y-intercept. The negative delta H of vaporization over R is our slope. Okay, 1 over T can be our x, and Ln of P is our y. Okay, so in this way, what are we going to plot? We're going to plot Ln of vapor pressure versus 1 over the temperature. And if we plot those entities, we actually get a straight line. So here is the derivation of the Clausius Clapyron equation, which I'm not going to go through at this time. But you can see here that if we plot Ln of vapor pressure versus 1 over temperature, we get a straight line where Ln of B is our y-intercept and our slope is given by negative delta H of vaporization over R. So if you plot this in Excel, you can actually get the slope as negative delta H of vaporization over R. So the delta H of vaporization is equal to negative times negative of the slope times R. So here I've done problem 12.4, okay, where I've plotted the temperature versus vapor pressure for this substance. So let's read this problem in example 12.4. The Clausius Clapyron equation leads to a convenient way to determine the heat of vaporization in the laboratory. We measure the vapor pressure of a liquid as a function of temperature, and we can plot the natural log of the vapor pressure versus inverse of temperature. We can then determine the slope of the line to find the heat of vaporization. The vapor pressure of dichloromethane is measured as a function of temperature, and the results are tabulated. From these results, determine the heat of vaporization of dichloromethane. So here we have temperature increasing in Kelvin by 20 degrees per point. We have a temperature of 200, 220, 240, 260, 280, and 300. And at each one of those temperatures, we've measured the vapor pressure for dichloromethane. Here we have those values, okay? So we're going to use an Excel spreadsheet to plot the natural log of the vapor pressure as a function of the inverse temperature, and then fit the points to a line, and Excel can do this for you. The slope of the best fitting line we find to be negative 3773 Kelvin. Since the slope equals the negative delta H of vaporization over R, we find the heat of vaporization in this way. The slope is equal to negative delta H of vaporization over R. So the delta H of vaporization is equal to the slope times R, and we found the slope to be negative 3773. And then we multiply that times R, and we get the delta H of vaporization as 3.14 kilojoules per mole. So you can see here that the slope was found in Excel. Alright, so here is how we actually plot this in Excel. First, you're going to enter the data, leaving a column in between. So here I've entered the temperature in Kelvin and the vapor pressure in torr. So the temperature in Kelvin, 200, 220, 240, 260, 280, and 300. The vapor pressure in torr, 0.8, 4.5, 21, 71, 197, and 391. Next, I'm going to put, right beside the vapor pressure, I'm going to put Ln of the vapor pressure here. And so I'm going to hit equals, and then I'm going to choose Ln, and then choose this cell and hit enter. Then I'm going to highlight the cell, hit Control C, and highlight these cells and hit Control V. So then I'm going to do a similar thing with the temperature. I'm going to hit equals here, then hit this cell, okay, and then, hit equals, and then 1 divided by, hit this cell and hit enter. Then Control C, drag down and hit Control V, and now we have our data. So then we can highlight these 2 columns, right click and choose plot. And that's how I got my plot. Alright, so that's how we can get the data from the using the Clausius Clapyron equation in the line form. And remember, ln of B would also give us our B for our particular substance in question. But there's also a 2-point form for the Clausius Clapyron equation that we can use. And we're going to see some examples with this as well. So the 2-point form is ln of P2 over P1 equals negative delta H of vaporization over R times 1 over T2 minus 1 over T1. Okay? And so what this is, and I actually need brackets here. And what this is going to do is I can use the normal boiling point for a substance, okay? Because I know that at atmospheric pressure, okay, that would be 760 torr, so I can plug in 760 for P1, and then I can plug in the normal boiling point for T1, and I have to know the delta H of vaporization for that substance. Then I can find P2, in other words, the vapor pressure at any temperature. So if I know the delta H of vaporization, and I know the normal boiling point for a substance, I can calculate the vapor pressure at any temperature by using the 2-point form of this equation. And we'll see an example of this when we work our example problems.